Hi everyone. So this first lecture is going to be a little bit of review from the week before spring break, but I know it's been um, a little while since we talked and probably a rather distracting week. So I'm going to start these first few lectures with a little bit of review, which should help with the homework, and we'll kind of ease into things gradually. So this lecture is going to be about area of triangle on a sphere. If you already know how to do it, then feel free to skip it. So if we've got a sphere, as you all know, a triangle can be formed by connecting three geodesic segments at three vertices. And remember, these geodesics are coming from a great circle, like that. And for the purposes of this talk, I'm really only caring about so-called small triangles. So those are the ones which kind of look and feel like triangles. So nothing weird. I know we spent some time talking about ways you could make things which technically satisfied the definition of triangle, but were kind of strange. Let's just ignore those for this talk. But if you're interested, fun exercise might be to see if the theorem still holds for those as well. So what is the theorem? Well, what we're going to prove is that the area of a small triangle, so just um, the usual triangles on a sphere, small triangle on a sphere depends only on the interior angles of the triangle. So I measure these angles, let's say they're alpha, beta, and gamma, and I should be able to calculate the area of the triangle on the sphere from just those angles. Now, notice that if you're used to working in Euclidean geometry, this is strange because in the plane, obviously there are triangles which have the same interior angles but not the same area, right? And so this is some new phenomenon that appears in spherical geometry. Turns out it works in hyperbolic space as well. Maybe I'll talk about that later. So the key tool to proving this theorem is the notion of a lune. And a lune, something that only really makes sense on a sphere, is the space enclosed by two geodesic segments meeting at an angle let's say alpha. So the picture is you have a sphere, and if I take two geodesic segments, of course they intersect twice, and I look at the space which they enclose. And that the interior angle there is going to be important. So let's label it alpha. So this space inside of here, this is a lune of angle alpha in this case. Okay, so an example of a lune, the example to have in mind, which is the one I have in this picture, is the space between two longitude lines. Oops. But of course, it could be any two geodesics, right? So we could have some other geodesics, like if I chose these two, then you can see here that there's actually 4 choices of loon coming from these geodesics, and each of these is a loon. Maybe I look at this space right here. That's a perfectly good geodesic, or sorry, that's a perfectly good loon. Okay, so that's the definition of a loon. And then the question that we did in class, which you might remember, is on a sphere of radius rho. So it depends on the radius. Let's let S sub rho be the surface area. Of the whole sphere. Then you can calculate the area of the loon in terms of S sub rho and the angle alpha of the loon. So I claim that the area of a loon with interior angle alpha is going to be alpha over 2 pi times the surface area of the whole sphere. Okay, so why is that? Well, it helps maybe to look at the loon from above. So let's imagine that our loon was formed by 2 longitude lines. So maybe I've got this as my loon, angle alpha here. I can rotate this sphere so that I'm looking at it as if I'm directly above the North Pole. So this is the equator line. And then from this vantage point, the loon looks like that, going down past the equator. So we can't see the southern hemisphere here. But it looks like this space. Maybe I'll draw the bottom too. So that's the loon. And we know that this interior angle here is alpha. Okay. And so what the claim is that the area of this whole loon is this quantity here. And why is that? Well, because the whole surface area of the sphere is given by S sub rho. And what is this loon? Well, it's just some fraction of the whole surface area. And what is that fraction? Well, it's determined by the angle, right? So if I went all the way around, if my loon kind of went all the way across the sphere, then of course the area would be the whole thing. But what fraction is it covering? Well, the fraction is exactly how far around I'm going, which is alpha in radians divided by 2 pi. That's the fraction that I'm going around. Okay, so just to make it super clear, again, the view from above is exactly this. So what fraction is this loon covering? Well, it's exactly given by the angle divided by the total amount of angle, which is alpha over 2 pi. So the loon covers alpha over 2 pi, this amount of the whole sphere, this fraction of the whole sphere. And so what's the surface area of the loon? Or the area of the loon is this fraction times the total surface area, which is S rho. Okay. Why is that useful for what we're trying to do, which remember is calculate the area of a triangle on a sphere? Well, the point is that if I draw a sphere, I'll draw a really big one here, and I draw a triangle on it, it's made, well, it creates some loones kind of naturally. So here's my triangle, and how do I get some loones out of this picture? Well, I'll use some colors. Hopefully this will make things more clear, not less. I'm going to extend these geodesic segments to the entire great circle. And anytime I have great circles intersecting, I get loones. Okay, so that's the picture. Now the triangle that we care about, I should probably label the angles. So call this angle alpha, this angle beta, and this angle gamma. We're trying to calculate the area of this. The first thing to notice is that there's kind of an identical copy of this triangle on the back side of the sphere where the dashed geodesics intersect each other. So you can see that, that triangle in the back right here. And that's because, let's pretend we're looking at the northern hemisphere right now from above. The southern hemisphere is kind of an identical copy of the northern hemisphere via the isometry, which is reflection through the center of the Earth, right? It's going to send this point to that point, this point to that point, this point to that point, etc. So you get a copy of this triangle in the back. And now to calculate the area, the point is that we know the area of loones, at least as long as we know the surface area of the sphere. From that, we can calculate the area of loones. And in this picture, I see a lot of loones. And in fact, for each of the angles that I've labeled here, I see a loone. So here's one of them. Picture is going to get a little bit messy, and I apologize. So that's the first loone going down to the back right there. So it doesn't cover the back triangle, it just hits it at a vertex. So that's the alpha loone. And then, well, let's do beta next. So there's a beta loone as well. By looking at the red and the blue geodesic and the area inside of them coming from the angle beta. And then there's the gamma loone as well. So that one. Okay. So I've got these three natural loones, which are related to my triangle in some way. And I know their area, so that's what's nice. So the area of loone alpha is alpha over 2 pi times the surface area of the sphere, S rho. And similarly for loone beta, it's just beta over 2 pi, surface area times S rho. And same with loone gamma. Okay. Okay, well, why is that useful? So far, it's not really. What we're trying to get is the area of this triangle. And what I notice here is that these loons I've drawn, they cover the triangle. In fact, they cover the triangle 3 times. The alpha loon contains this triangle, the beta loon does, as does the gamma loon. So I've covered the triangle 3 times. And then the next thing I want to point out is that I can actually cover the whole sphere with these loons. I haven't yet, but if I add a few more, and I'm just going to add the minimal number I need, which is really 3 more, and you can kind of convince yourself of that by just looking at this top half. You can see that the other parts that are missing are sort of like this part, and this part. Well, those are also loons. And so if I include those loons into my picture, then I will have covered the entire sphere with some overlap though. So first, here's another alpha loon right here. And I'm not going to draw the back part because I don't want the picture to get too messy. But this other alpha loon goes back. And here's another beta loon right here. And another gamma loon right there. And now the entire sphere is covered. Okay. So the total, well, I should say the whole sphere is covered by 6 loons. 2 of them look like L-alphas. So 2 L-alpha loons, 2 L-beta loons, and 2 L-gamma loons. Okay, and so you might guess that the surface area of the sphere is equal to the area of all these loons added together, and that's almost correct, except these loons have overlap. And so you're overcounting then. You're getting too much area if you add all the loons together. And so the total surface area is equal to S rho, we know. That's equal to the sum of the area of all the loons. So this is 2 times L alpha plus 2 times L beta plus 2 times L gamma. But we've overcounted, so minus some overlap. So minus something. Right? Now how much overlap do we have? What to put in this question mark to get a true equation? That's the next question. And the thing that's going to connect this to triangles is we notice that the overlap occurs exactly on the triangle. And so the area of the triangle is going to go into this question mark here. So how much overlap do we have? Well, on this triangle, notice that each of the original alpha, beta, and gamma loons, they all cover the triangle. And so we've covered the triangle 3 times, which is, overlapping by 2, right? We covered it once, and then we over-covered it 2 more times. And there's the exact same picture on the reverse side of the sphere, where in that case, the triangle in the back gets overcounted because of the 3 extra loons we added. They all cover the triangle. And so all in all, the area of this triangle, notice it's the same area for the front triangle and the back triangle because there's an isometry that sends one to the other, so they're congruent. All in all, we've covered this triangle 6 times. And 2 of those times, we actually want to count for the total surface area. And then there's 4 extras. And so the overcount is going to be 4 times the area of that triangle. Minus 4 times the, well, I'll call it A, where A is equal to the area of the triangle with angles alpha, beta, and gamma. Okay, and what I want to do now is solve for A in this equation, right? So A now is equal to, okay, well, I can move it to the left side here, and I'll move this to the other side there. So A, well, 4A at least, is equal to 2 times L alpha plus L beta plus L gamma minus S rho. And I know, remember, the area of these loones in terms of S rho. And so this is 2 times alpha over 2 pi times S rho plus beta over 2 pi times S rho plus gamma over 2 pi times S rho minus S rho. And so what I get, if I divide by 2, is, well, okay, what do I want to do? Let's pull out S rho and divide by 4. So A is equal to S rho divided by 4 sorry, having trouble doing math. All right, so if I divide by 4, that's the same as canceling this, dividing by 2. So I am getting, this seems wrong. I should look at my notes. Nope, it's correct. Is it correct? Let's see here. Guess I'm off by a sign. What happened? Sorry. Oh, my notes are wrong. This is correct. So, sorry, I was doubting myself. So alpha over 4 pi. What am I doing? Okay. I am going to factor out a 4 pi here. Anyway, this is algebra. You all know how to do this. And I get alpha plus beta plus gamma minus 1. Okay. Exercise, check that this is correct. But I think it should be. And this is the formula. So this is the area of a triangle, and notice that it depends only on the surface area of the sphere, which in turn depends on the radius of the sphere, as well as the angles of the triangle, alpha, beta, and gamma. If you know the formula for the surface area of a sphere, you can simplify this. So a fact that you can prove using Calc 3 techniques, it's kind of a classic Calc 3 problem using spherical coordinates, of course, is that the surface area of a sphere of radius rho is equal to 4 pi rho squared. So we can, okay, that's why that 4 is okay. And so we can plug that into the formula above, and the 4 pi's cancel. And finally, the area of a sphere is equal to rho squared times alpha plus beta plus gamma minus 1. Let's do some sanity checks just to make sure this is reasonable, especially since I confused myself on the algebra. Well, the first thing is it positive? Because we know that the area should be positive. Yes, right? Because the interior angles on a sphere are always summing up to something larger than pi. In degrees, remember, the sum of the interior angles on a sphere is greater than 180. Oh my gosh, this is supposed to be a pi. I might re-record this depending on how lazy I am. Why is that a pi? Why is that a pi? Oh, because I factored out a pi here, right? So this should also be a pi. Probably not going to re-record it since this is review anyway. Okay, sanity check. Is it positive? Yes, because on a sphere, sum of the interior angles of a triangle is greater than pi. So alpha plus beta plus gamma is greater than pi. Okay, and that means that the quantity in parentheses in this formula for area is positive. Rho is the radius of the sphere, that's positive, so we're always getting a positive formula for the area. Second sanity check is if we had a 90-90-90 triangle where they were all right angles, well, we know the area of this in terms of the surface area of a sphere, because this is exactly 1/4 of a hemisphere, so 1/8 of a sphere. So in this case, the area should equal 1/8 times the surface area of the sphere. Does it? Well, let's check. So, does it work with our formula? So in this case, alpha, beta, and gamma are all equal to pi over 2. And so our formula says that we should get S rho over 4 pi times 3 times pi over 2 minus pi, which is equal to, this is pi over 2, right? And so what do I get? I get pi over 2 divided by 4 pi, which is 1/8. So I get S rho over 8, which is what I wanted. Okay, so sanity check, is it positive? Yes, and it works for our favorite triangle on a sphere, which is the 90-90-90 triangle, but we're using radians, so I'll call it the pi over 2, pi over 2, pi over 2 triangle. Okay, that's it. Thank you for listening. Try to turn the video